Hi everyone, this is part 2 of your 7.1 Simplifying Trigonometric Expressions video. I'm just going to show you one example from number 7 and then I will get you started on number 8. So what you can see is that in part A, it's actually already started for you. So the prompt reads, not all trigonometric expressions can be efficiently rewritten using algebra. Sometimes geometric diagrams are more useful. This gets at, by the way, we've been talking about having some fluidity between the unit circle and an in-unit circle, and the graphs that you see of trigonometric ratios or the inverse trigonometric ratios representing angles. And this is one of those times. So when you see, for example, inverse sine of 2/3, that's actually representing an angle, because you know that this is the ratio of sides, and when you have the inverse sine, it would be equivalent to writing the sine of some angle equals 2/3, and when you write inverse sine of 2/3, then that represents that angle. And so what you have here is you have some triangle, some right triangle with a reference angle of theta. And you know that according to that reference angle of theta, the opposite side is going to, and the hypotenuse will have a ratio of 2/3. So in this triangle, we went ahead and labeled the triangle with 2 and the hypotenuse with 3, but you could actually choose any ratio that is equivalent to 2/3 as well. And then what you're trying to find is the cosine of that reference angle theta. And so you're trying to find the ratio of the adjacent side over the hypotenuse when this is your triangle. One thing that you really need to check is whether your triangle is even allowed. And what I mean by that is that sometimes students will draw diagrams of triangles that actually aren't triangles. They just look like it. An example of that would be like if I said inverse sine of 3/2, that seems really similar to this one. And yet if you were to draw the triangle where you have some reference angle and you were to draw your opposite side 3 and your hypotenuse 2, this is not a possible triangle. This is actually not a possible triangle. Just because you drew it that way doesn't actually mean it technically exists. And I'll show you in a second how you can determine what would be a red flag for this particular triangle. But in this case, we know that we need to solve for that adjacent side because we are trying to find the cosine of this angle theta. And so when I set this up, I can see that I have 2 side lengths and I need to set up the Pythagorean theorem. I have the legs, and so I have 2 squared plus whatever my adjacent side is. Let's just call it A squared, and I know that that equals my hypotenuse squared. And so I have 4 plus A squared equals 9, and then A squared equals 5. And so that tells me that my adjacent side is the square root of 5. And it's actually easier to, or not easier, but it's preferred to leave that exact. However, you can also just, to note, it's always good to have an idea of how to approximate radicals. So the best way to do that is to think, all right, I know that the closest whole square numbers are 9 and 4. And 5, if you think about 6, 7, 8, is about 1/5 of the way, right? Difference between 9 and 4 is 5. So the square root of 5 will be about 1/5 of the way between the square roots of 4 and 9. So you know that the square root of 4 would equal 2. The square root of 9 equals 3. And since this is about 1/5 of the way, you can actually approximate this as around 2.2. But again, this is the exact side. That's not our final answer, of course, because we need to find the value of this expression. So the answer, your final answer, is going to be the adjacent side of root 5 over your hypotenuse, which is 3. And then I always make sure, does my answer make sense? So if I think about 2.2 over 3, that's a little over 2/3. So that means my adjacent side is about 2/3 of my hypotenuse. And that does indeed make sense in terms of, making sure I don't have an adjacent side that's bigger than the hypotenuse, or that I have an unreasonably big length or an unreasonably small length, etc. So always do a double check to make sure your answer seems reasonable. Now, a red flag, if you were to see something like this triangle, would be that if I were to set up the Pythagorean theorem, for example, I would get 2 squared, that hypotenuse equals 3 squared plus a squared, and what I get is 4 equals 9 plus a squared, and I get that a squared equals -5. Well, that's a big red flag because you have a negative length. And remember, even if we were to draw that, even if that triangle was here, the length is still positive. That's still, we're not going to have an imaginary length. So big red flag if you get something algebraically, you make sure you did your setup right and you get something suspicious like this. So again, that doesn't work. This is a triangle that wouldn't exist. So then in number 8, it says using your strategies from the previous problem to write an algebraic expression not involving trigonometric ratios for the sine of inverse tangent of x, and assume that x is greater than 0. So basically just assume that you have a ratio of side lengths that is positive. And so again, I knew that was a ratio of side lengths because I'm looking at the inverse tangent. So I know that that is a ratio, and the output or the value of the expression would represent an angle. So that tells me if I were to draw a diagram that I'm looking at some ratio. This has to represent a ratio of side lengths because it is the inverse tangent. So I'm looking at the sine of some angle here. Let's go ahead and call it alpha. That's alpha. So we have alpha, and then the x value, we know that tangent of any angle equals the opposite side over the adjacent side, which means your ratio of your opposite side and adjacent side better be x over 1 or an equivalent value. So I can label this as x over 1. And then you want to make sure that you find the sine of that. And so you can see that similar to this problem above, you're going to have to do some solving for that to find your final answer. So remember, with trigonometry, always remember to come back to your right triangles and that you have your reference angle diagrams that can be useful, or your graphs. Maybe you have sine or cosine. Maybe you have tangent. So you should feel some fluidity between all of the representations that we've talked about in order to be able to successfully analyze any trigonometry problem. Thank you so much for watching, and I hope that you found this valuable and enjoyed it.